All right, let's dive into something you see all the time, probably without even thinking about it. We're going to pull back the curtain on a real mystery. Why does light, which we all think travels in a perfectly straight line, sometimes decide to just bend? I mean, who hasn't seen this, right? You stick a perfectly straight pencil or a straw into a glass of water, you look at it from the side, and boom, it looks like it snapped right in half where it hits the water. It's such a simple little illusion, but it's actually a clue to something really fundamental about how light works. And hey, it's not just about pencils. This effect is everywhere once you start looking for it. It's why the bottom of a swimming pool always looks way shallower than it actually is. It's why if you put a slab of glass over a book, the letters seem to kind of float up towards you, or why a lemon in water suddenly looks jumbo-sized. Believe it or not, all these weird optical illusions, they all boil down to the very same scientific idea. So what's the deal? What's the secret principle behind all the magic tricks? Well, it's got a name: refraction. And once you get what refraction is, all those everyday mysteries suddenly start making a whole lot of sense. Okay, so here's the official definition. Refraction of light is just the phenomenon of light changing its direction when it travels from one transparent material or medium to another. Now, the key word, the one you got to remember, is obliquely. That just means at an angle. See, if light hits a new material perfectly straight on at a 90-degree angle, it just goes right through. But at any other angle, it's going to bend. But why? Why does light bend at all? Well, the entire reason, the whole culprit, is a change in speed. You see, light is the universe's ultimate speedster in a vacuum. But the moment it enters anything else, air, water, glass, diamond, it slows down. And when light crosses that boundary from one material to another and its speed suddenly changes, it's forced to change direction. To really get this, let's follow a single beam of light on a classic journey, passing right through a rectangular block of glass. This little experiment is perfect because it shows us not just one bend, but two. So check this out. The light ray that comes in, we call that the incident ray, hits the glass. Bam, it bends. Now it's inside the glass, and we call it the refracted ray. Then, when it leaves the glass on the other side and pops back out into the air, it bends again. That final ray is called the emergent ray. So let's break down those two bends, because this is where the magic happens. First, when light enters the glass, it's going from a rarer medium, air, to a denser one, glass. Because of that, it actually slows down and bends toward this imaginary perpendicular line we call the normal. But then, when it leaves the glass, the total opposite happens. It's going from denser to rarer, so it speeds back up and bends away from the normal. The two bends are perfectly equal and opposite, which is pretty cool. Okay, so we know it bends, but is it random? Or can we actually predict how much it's going to bend? Well, you bet we can. This isn't chaos, it's physics. The amount of bending is controlled by a really precise law and a specific property of whatever material the light is passing through. The rule that governs this is called Snell's law. Now, it sounds a little intimidating, I know, with all the talk of sines and angles, but the basic idea is super simple. For any two materials, like air and water, there's a fixed relationship between the angle the light comes in at and the angle it bends to. That relationship is always a constant value. And that constant value, that's what we call the refractive index. Seriously, the best way to think of it is as a light bending score. Every transparent material has one. And it connects right back to speed. The refractive index, which we represent with the letter N, is literally just a ratio. The speed of light in a vacuum divided by the speed of light in that specific material. So let's look at the leaderboard, shall we? You can see air is barely above 1, which means light hardly slows down in it at all. Water clocks in at 1.33, glass is a bit higher at 1.52. And then, whoa, look at diamond, way up there at 2.42. The rule is simple. The higher the number, the slower the light, and the more that material bends it. Okay, we have to talk about diamond for a second. That number, 2.42, what does that even mean? It means that light is forced to travel almost 2.5 times slower inside a diamond than it does zipping through the vacuum of space. That massive, massive slowdown is what causes the extreme bending that gives diamonds their incredible fire and sparkle. Okay, hold on. This next part is super important because it's a really common mix-up. When we talk about a medium being denser in optics, we're not talking about how heavy something is. We're talking about something different, called its optical density. Here's the breakdown. An optically denser medium just means it has a higher refractive index, and light travels, you guessed it, slower. An optically rarer medium, lower refractive index, so light travels faster. It's all about the speed of light, period. It has nothing to do with weight.
And this is the mind-bending part right here. Just because something is optically dense doesn't mean it's physically heavy or has a high mass density. The two things just aren't the same, which leads to some really weird, counterintuitive results. And here is the absolute perfect example of this. Kerosene is optically denser than water. Its refractive index is 1.44, while water's is 1.33. So it slows light down more than water does. But we all know what happens if you mix them, right? The kerosene floats on top. That's because its mass density is lower. It's just the perfect illustration that what makes something optically dense has nothing to do with what makes it float or sink. All right, let's do a quick recap of the big ideas here. 1. Refraction is just the bending of light. 2. It's all caused by a change in speed as light hops between materials. 3. When it enters a denser medium and slows down, it bends towards the normal. 4. When it enters a rarer medium and speeds up, it bends away from the normal. And finally, the refractive index is our light bending score for any material.
And that leads to a really cool final thought. We know that when light goes from a dense to a rare medium, it bends away from the normal. But what if you increase that angle? What happens if you bend it so much that it can't get out? What if the light gets trapped, bouncing around inside? But that's a whole other amazing phenomenon for another day.